During my time as a computer science student, I've been captivated by many topics: networking, computer graphics, computer vision. There are an infinite number of options. Amongst all of these, though, none have quite caught my attention like the SLAM problem. Simultaneous localization and mapping, or SLAM for short, is the computational problem of constructing or updating a map of an unknown environment while simultaneously keeping track of an agent's location within it. Now, this fascinated me as soon as I read it. So rather than waiting for someone to give me the opportunity to work on their SLAM system, I decided to create my own. This is CARtographer, a differential drive robot with a fully functional SLAM system that I have built from the ground up. I've written all the software myself. From the SLAM system to the perception system, I did not rely on any libraries to do the heavy lifting for me and implemented it all myself. All the hardware is also custom assembled by me, including the wiring and the chassis. This is a project I've worked very long and hard on, and I'm very excited to present it.
Let's briefly talk about some of the main software components of CARtographer. Perception is an essential component to any SLAM system. This is how the robot sees. First, we start with a real-world environment, then this is scanned by the LiDAR scanner placed on top of CARtographer. The raw points are then sent to be processed by the ransack algorithm, which allows us to find straight lines in the data. Then those lines are sent to the data associator, which separates good landmarks from bad ones and matches incoming ratings to existing landmarks or decides to create a new landmark. The final landmarks are sent to the SLAM landmark database, where they are kept and tracked for the runtime of the system. When new lines come in from the ransack algorithm, they are paired with the closest existing landmark in the system using the nearest neighbor approach. Then we use Mahalanobis distance to decide if we can reasonably associate these two landmarks, based on their variances and the distance traveled by the car since the last time step. If the Mahalanobis distance is within some threshold, we allow these points to be associated and send them to be processed in the SLAM database. Here's a real-world example of the data pipeline. The car takes a scan of the room that you see on the left, the LiDAR sees the points that you see in the middle, then Ransack extracts the walls as illustrated by the green lines on the right. The cognition piece of the stack is a dynamic extended Kalman filter. A Kalman filter is an algorithm that uses a series of measurements observed over time to produce state estimates that are less prone to errors from measurement noise or other inaccuracies. In this application, the state is defined by the robot pose as well as the global XY coordinates of the observed landmarks. This diagram shows us the basic flow of the Kalman filter. We have an initial state estimate and a measurement, in this case LiDAR data. Then we pass it through the Kalman filter and receive a state estimate that is a more accurate representation of the true state of the robot. Then we use this new state estimate in the next iteration and repeat the process. In a traditional extended Kalman filter, the size of the state remains the same over time. However, in our case, we must add new landmarks as we see them, so our state vector grows over time.
Before showing CARtographer in action, let's briefly talk about landmarks and the geometry of the map. Landmarks are what will allow the robot to localize itself in its environment. For this project, we consider walls as landmarks. Take a look at this picture. On the left is CARtographer in physical 3D space, and on the right are the lines it sees around it. Also, the car's orientation is described by the X and Y axis labels you see on the screen. In the actual SLAM system, each wall is represented by the point on that wall that is closest to the origin. This is much more efficient than tracking multiple points that make up a line. So when you see a landmark point in the following demonstrations, remember that it represents a wall. First, let's demonstrate the car's ability to localize itself through periodic updates of its observed landmarks. On the left, you see CARtographer in physical space, and on the right is a visualization of CARtographer's internal map. The car begins at its initial position. We take this as the origin and mark it with the green X you see in the middle of the screen. Now, the car is represented by the blue dot, which is placed on top of the origin. Let's take some scans of our environment and watch as the landmarks appear. Let's stop scanning. The landmarks are represented by the green dots, and the red ellipses around them are error ellipses, representing the system's confidence region of that point. As you can see, the system is quite uncertain of the position of these landmarks, as indicated by the large size of these ellipses. Now, let's see what happens when the car moves in any direction without taking any scans of its environment. As you can see, the system is now very uncertain about the position of the car because we are currently relying solely on the motion model. The uncertainty will continue to increase with more movement. Now, let's see what happens to the uncertainties of the car and the landmark positions as we take more scans of our environment from this new position. As you can see, the system has grown more certain about both the position of the car as well as of the landmarks. The area ellipses will continue to shrink further and further as we take more scans. Now, let's see if CARtographer can perform loop closure. For this demo, the system will constantly be taking new scans to continuously update the map, as opposed to the periodic updates of the previous demonstration. Once again, we begin at the origin. With the system constantly taking new measurements, we can watch and see how the uncertainty of landmarks rapidly shrinks shortly after their appearance in the map. On top of that, landmark uncertainty remains small after the system becomes confident in their positions. Now let's move to a position where the currently observed landmarks are not visible to CARtographer. At the moment, the system is very uncertain about the position of the car in the map, as indicated by the very large area ellipse surrounding the blue dot. This is because the walls that were previously observed are currently out of range, and thus CARtographer is forced to rely solely on the motion model. Now, let's return to a position where the previously observed landmarks are visible again. As you saw, the uncertainty of the car's position rapidly shrank as soon as the previously observed landmarks were visible again. This is essentially a primitive form of loop closure. The system recognized a previously visited location and used that information to correct and reduce errors accumulated during navigation. That was a short demonstration of CARtographer and his SLAM system. In the future, I want to make CARtographer fully autonomous, able to navigate new and old environments without any assistance. Since the SLAM system is already implemented, this will just come down to solving a path and motion planning problem. I also want to hook up a camera to CARtographer and give him vision. Vision combined with LiDAR data will be extremely feature-rich and will enable a significantly improved SLAM system, as well as a navigation system. If you want any more details about CARtographer, I've created a design document going into further detail about every aspect of the design. You can find it linked in the description. I hope you enjoyed this short video. Thank you for watching.